Hey guys, welcome to our first video on continuous functions. A continuous function is basically a function that doesn't have any problems in it. You can basically draw the graph without ever picking up your pencil to get to a different location on the axes. So there's three types of discontinuous three types of discontinuity. The first one is going to be an infinite, which I'm sure you guys have seen. It's when the denominator is undefined at a certain location, and we say that we have a vertical asymptote. The second one is a whole, and I'm sure some of you seen it in pre-calculus. It's basically when the top and the bottom factor and you have something in common and you could cross off. And then jump, which we see with piecewise defined functions. Okay, I thought it was very important to start off with things that are continuous. This will help us with our piecewise functions. So this is a line, we know that. And we know that lines are continuous. There's no problems with lines anywhere. This is a parabola, and sorry about the handwriting. The parabola, we also know there's no problem. You can draw it, not the way I did. You could draw it without picking up your pencil. This is a cubic function, so there's no problem here. And this is the sine graph and the cosine graph. Now, one thing that's really important that will help you guys determine if something is continuous or not is that all these are basically, these three are polynomials. There's no denominator. In other words, they're not rational functions. So we have no place where they're undefined. So that's really important. Sine and cosine doesn't have a denominator, obviously, other than 1, where there could be a problem. Okay, so those are the only places where you'll see problems. So great, let's move on. Here are my three types of discontinuity that I mentioned in the beginning of the video. The first one is this guy right here, f of x equals 1 over x minus 4. We know x cannot be 4. If you go to graph this and you go to x equals 4, you'll see there's a vertical asymptote. And that vertical asymptote says this is an infinite type of discontinuity, okay? This one here, for the second one, x squared minus 3x plus 2 over x minus 1, you might also say, wait, is that also an infinite because it's x cannot equal 1? Well, the difference between this guy and this guy is that the top is factorable. So let's factor the top, okay? So I'm going to factor him down here. You get x minus 2, x minus 1, and what you notice is that they're common in the numerator and denominator. Once they're common in the numerator and denominator, you cross those off. You say x still cannot equal 1, and there's a point discontinuity. So if you watch my limits video, you'll understand some of this better. So 1 gets plugged in, comma, negative 1. So there's a point discontinuity at 1, comma, negative 1. So this function here is identical to x minus 2, except for at the point 1, negative 1, there's a hole. So that's the graph, and that's what it looks like. In the third problem, this is our piecewise defined function. It says for x to be less than negative 1, I want you to use the guy here, okay? So once we plug in, so I know from the beginning that this is a line, just like I was trying to show you guys here. So this is a line, and I know it's continuous everywhere. This is a parabola, and I know it's continuous everywhere. The problem is that the line in the parabola broke at some point here. So what would happen at 1 with the line? Well, I get 5, because 1 times 2 plus 3. What would happen here? I get 1 squared is 1. Since these two numbers do not match, that means that there's a jump in the graph. So this is obviously not accurate, but I want to show you. At 1, one of them goes to 1, and the other one goes to 5. So you might have something like this, and then you might have something like this. There's a jump between those two. So those are your three types of discontinuity. So let's try the next problem. So for a function to be continuous at a point, its limit must exist at that point, and the function must be equal to the limit. So it has to be defined there. So let me show you what I mean by that. Here's a piecewise defined function. So this is what we're going to do. We know again that this is a line and it works everywhere. That's what I said in the beginning of the video. We know that this is a parabola, it works everywhere. That's what I said in the beginning of the video. But we broke it up so we can only, so we have to just observe it just at this point at x equals 1. So, what is the limit as x approaches 1 from the left of this function? So this is, left means less than or equal, basically just a little bit less than 1, so 0.9999. The limit is approaching 1. What is the limit as x approaches 1 from the right? Well, I hope you guys seen the videos on limits. That goes in there because that's a little bit more than 1, so that's going to be 1. Now these two match, but that only means the limit as x approaches 1 of f of x is equal to 1. I have to now see, does f of 1 equal 1? And it sure does. The way that we take a look at that is you're looking for the equal sign, okay? So that's this guy here. When you put 1 in here, it also equals 1. Therefore, the function is actually continuous. So let's try another problem. Here we go. The limit as x approaches 2. Once again, this is a line, this is a line, this is a line. Lines are continuous. The only thing we care about right now is analyzing x equals 2. So the limit as x approaches 2 from the left, we're going to use less than 2. So that's going to give you 3 times 2 is 6 plus 1 makes 7. The limit as x approaches 2 from the right is going to be 2 times 5 minus 3, that's 7. Now you have to just make sure that f of 2 equals 7, which it does. It's right there. Therefore, this is continuous as well. Okay? Let's try one more. Now, this is a parabola, this is a line. They both work everywhere, except for now we broke it up, so we have to analyze 3. So, the limit as x approaches 3 from the left of this function is going to be 18, because it's 3 squared times 2. The limit as x approaches 3 from the right is 15. These guys don't match. Since those two don't match, the limit at x approaches 3 doesn't even exist. Does not exist, so it's not continuous. It's actually a jump, okay? So how does that look like? At 3 and less, I meet at 18, but because there's an equal sign under, I'm gonna fill in that circle. I hope you guys remember this from pre-calc. That goes like that. For 3 or more, this is at 15, so that's gonna be open circle, and that's a line. So that goes like that. There's a jump between. I believe I have one more problem. Yes. So this problem here, the only place that it doesn't work is at x equals 5, right? So x cannot be 5 here. So my question, I guess, because I didn't write a question, is this function continuous on the interval negative infinity to infinity, which means the entire real values? And it's not, because it doesn't work for 5. What kind of discontinuity is it? Infinite, okay? What about now? Well, I made my interval 7 to 10, open interval, 7 to 10. The only place this doesn't work is 5. Well, 5 is not in the interval, so actually the function is continuous on this interval. All right, so that's basically the gist of continuity. I'm going to make about 3 or 4 more videos with just examples, so I hope you come back and watch some more.